Machine learning models are partly wrong and they're partly right. We need something called error, sometimes referred to as loss or cost, which can quantify how wrong is a model. For this, we'll stick to the discussion of supervised learning, and so that means regression, and later we'll look at classification. Now this video will show Python code, but I'm not going to explain or talk about it. If you'd like to look at the code, please check the video description, and I have the notebook that I'm looking at here. First, regarding regression, let's look at areas in California. So we have a dataset where we have two columns. The first is total number of bedrooms, and the second is total rooms. So each row of data is an area in California. And so for each area, we can count the total number of bedrooms in all of the houses, and we can also count the total number of rooms, which is bedrooms plus all of the other types of rooms as well. So for this area, which is just given by an ID of 0, we have 1,283 total bedrooms, and we have 5,612 total rooms in that area. We can plot all different areas on a scatter plot as follows. If we put total bedrooms on the x-axis and total rooms on the y-axis, we can plot each individual point given their total bedrooms and total rooms number. So this point here is an area in California with a total bedrooms value equal to 5,000 and a total rooms value equal to roughly 17,000. We could construct a linear regression through the data, which would draw a line through the points like this. That way, if we had a total bedrooms value for a new area in California, you could actually use the linear model to predict the associated total rooms value given the model. So if we were to create that linear regression, we would be left with this line here. Using this model, we can plug in some total bedrooms value and predict the associated total rooms value. If we had, say, a total bedrooms value of 5,500 and we wanted to predict what the total rooms value would be for that total bedrooms of 5,500, well then according to the model, it would suggest that our intersection would land right here, which means we would predict a total rooms value of roughly 25,000. For any single total bedrooms value, we can look up the corresponding total rooms prediction according to the model. But the model is not always right. As we can see, there is a vertical distance between the true total rooms value for this point and the predicted total rooms value according to the model. For this point, our model was this vertical distance wrong, or there was this much error. And for this point, there is this vertical distance between it and the model, and so there is that much error. We can simply calculate the vertical distance between the observed total rooms value and the predicted total bedrooms value for all of the points. So we take this value and we subtract what we predicted for the model, and then we get a distance between the point and the model. Now, as you can see, sometimes the model underestimates, as in the true point is actually higher than the model, and sometimes the model overestimates, as in sometimes the model is actually higher than the observed value. We have error or wrongness in both directions. If we don't concern ourselves with which side of the model the points are on, whether they're above or below the model, then we can just look at the distance between the model and the points. To get a measure of total error for our model, we can look at all of the distances between each point and the model. So we look at this distance and this distance and this distance and every single distance between the point and the line. If we were to do that, we would be left with a distance for every single point. Then, to get a measure of total error for the model, you simply sum up all of those distances, and that would be one big number, which represents how wrong our model is. In fact, if we were to do that, we would see that in total, our model has an error of 8,485,140. If you sum up the distance between every single point and the model, you would be left with 8,485,140. We aren't really concerned about the specific value of this number. What it means is that the bigger it is, the more error we have. And if we were to create a different model, say a nonlinear model, that approximates it a lot closer than the linear model, in fact, many times this model actually goes straight through all of the points, having zero error in those cases, well, that model would have a less error of 6,987,989. So that was the case for regression, where we are trying to predict a continuous or numerical value. Since total rooms is a numerical value, it is a regression problem. Technically speaking, it's actually not a continuous or numerical value since it only takes on whole numbers like 1, 2, 3, and onward, but you can approximate it, and in these cases, you generally simplify it to a regression problem. But the same ideas hold for a classification model, things just look a little bit different. So in this case, let's look at the mood of some teenagers. So I made a graph where we have green represents happy teenagers and red represents angry teenagers. On the x-axis, I have their size of lunch, which is in calories, and on the y-axis, I have their size of breakfast in calories as well. So this point represents an individual that is happy and had a lunch that was 700 calories and a breakfast about 250 calories. We could make a classification model where we try and predict whether they are happy or angry based off of their size of lunch and their size of breakfast. So no longer is this axis representing the output or what we are trying to predict. This is also an input or something that is helping us create the model. So we'll make a model that tries to use their size of lunch and their size of breakfast to try and predict whether they'll be happy or angry. Like before with the linear regression, we can make a linear model that instead draws a linear decision boundary. So here, anything painted in this red shade here, that means the model is going to predict that they will be angry. And anyone over here in blue, painted over here, that means the model thinks that they will be happy. Any point in red still represents that they were angry, and any point in green still represents they were happy. And the x-axis still represents their size of lunch in calories, and the y-axis still represents their size of breakfast in calories. So if we look at this point here, we can see that the model predicts it is going to be angry because the shade of this is red, except the point is green, meaning that the model got this point wrong. Similarly for this point, the model thought that it would be happy because it shaded it in blue here, except actually this individual was angry, and so the model got this wrong as well. But for any red point that lies in the red region, that means the model got those right, and any green point lying in the blue region, the model got those right as well. So as we can see, more often than not, the model got them right. It occasionally got stuff wrong, but most of the time it was correct. So like before, we can get a measure of how wrong the model is. The model is wrong here, 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 as well as here, 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 and many other points, so we can simply sum up the amount of times the model is wrong. And that's a great measure of how good or bad our model is. If we were to sum the amount of times the model was wrong, we would be left with the number of 18, which doesn't really mean much unless we know how many points are in the dataset. Since there is 100 total points in this dataset, we can calculate that the model got right 82 out of 100 times, and so it has what's called an accuracy of 82%. Now, like before, we can create a nonlinear model. And so if we were to do that, we would now be left with a very weird decision boundary. So still, anything that's painted in red, we are predicting that it is angry, and anything in blue, the model's predicting they will be happy. It just looks much different because it's not a smooth line, and that's what a nonlinear model would do. Now, since these are very hard to draw, the computer might actually look a little bit different than it truly is. But if we were to count its errors, we would see that the model gets 0 errors. And so this model has what we'd call a perfect accuracy. All 100 of them it got correct, and so it got 100% of them right. If that was helpful, make sure to drop a like and subscribe to the channel if you're not already, and I'll see you next time.